Good afternoon, everyone. It's a real pleasure to be able to present this work on inflatables here today. It's actually a real honor to be able to do it on the cusp of the 50th anniversary of the turbulent year of 1968 here in Paris, where inflatables became assumed as the architectural identity for counterculture and protest culture. So it's a real honor to be able to kind of talk about and return inflatables to Paris today. I'm going to talk a little bit about the context of this project, then identify the particular research question, talk through the methods, and then talk through some of the evaluation processes, and then talk about further collaborations that this work has spawned. The primary context is that this is work coming out of CETA research, funded by the Sapir-Aude Elite Researcher Grant, which was awarded to Professor Mette Ramsgaard Thompson in 2013. This is funded by the Danish Council for Independent Research. You can see here that over the last 4 years, this has spawned a series of projects. There are 6 projects in total, or 6 primary built projects. We have the Rise on the left, we have Stress Skins, which you've already seen today, we've got Hybrid Tower and Hybrid Tower 2, then we have Lace Wall, and we have A Bridge Too Far, which I think we'll be hearing a little bit about this afternoon. The kind of questions that complex modeling is asking is that it's really about investigating the infrastructures of our digital design models. And this is with a view towards supporting greater feedback between discrete scales of design consideration. So we're identifying 3 scales. The first is the scale of the structure, the second is the scale of the component, and the third is the scale of the material. The project's also focusing on the challenge of integrating material performance as an opportunity to cultivate new horizons for sustainable building practice. And the project has 3 primary objectives. The first is about greater design engagement through strong feedback between these scales. The second objective is investigating how computational tools allow a design engagement with dynamic modeling or simulation, and to do so in relation at the intersection with complex interacting systems. So we're looking a lot at hybrid structures. And then the third point is about how it is that through these computational tools we can still retain some of the intuitive, creative and communicable dimensions of architectural design practice. The other context is prior work with pneumatics. And the reasoning for this is being called Phil Ayres, there's a certain air of destiny about doing research in pneumatics. It's not so much a name, it's more an instruction. If you're looking for something more rational as a set of arguments, we're very interested in how the use of air as a ubiquitous material can be used to form materials through plastic behavior, but also to switch materials through elastic behavior. Now, the particular paper that's in the proceedings and part of this conference is focusing on the question of the cutting pattern. And this is of particular interest. If we look a little bit at the idea about membranes in general, we know that mechanically stressed membranes tend towards anticlastic curvature, class 3 there, whereas inflatables tend towards synclastic curvature, class 1. But what's interesting is that the membrane starts to become a steering device towards achieving types of curvature that particularly pneumatics doesn't naturally want to conform to. And we know this from the ubiquitous inner tube, where we see we've got positive, 0, and negative Gaussian curvature demonstrated there through the membrane. One of the other interesting points about the cutting pattern, particularly in relation to inflatables, but more generally in membrane architecture, is that it sits at the intersection between concerns of performance and concerns of aesthetic. And what's really interesting is when we look at the prior art and the prior manifestations of membrane architecture, we see that they tend to conform to a certain regularity of pattern. There's an aim at trying to reduce the deviation between individual strips and to try and create certain forms of symmetry. It's interesting that there's an engagement in perhaps looking at the surface qualities of these to try and perhaps move away from that, but underlying the Ayres forest from 2009 is still a very, very regular cutting pattern. When we're looking at a hybrid, pneumatically stabilized membranes with nets, we see that the net also begins to conform to quite regular patterning. We see here in the work of Frei Otto, we see this in the work of the US Pavilion in the Osaka World Fair, which is a really interesting reference in terms of the intersection between computation and material. It was using highly advanced materials developed by NASA, tightly woven glass fiber, and also working with deep analytical computational processes. But we see in the surface there that we've got very, very regular cells. And this is also the case with something like the Tokyo Dome, another air-supported structure. Interestingly, the air pressure internally is equivalent to the difference between being on the ground floor or the 9th floor of a building, so almost imperceptible, and yet you have this amazing structural capacity to hold this roof up. It's quite a nice roof as well. We start to see that we're moving away from the individual cell to these longer cells, but still there's a very strong regularity of pattern. Now, if we begin to intersect these kind of references with new computational tools, or computational tools that have been transferred from computer graphics towards architectural production, particularly here through this paper by Najur and Steinfeld, we see how the utilization of weighted mesh representation methods and mesh segmentation might actually become a very interesting point of intersecting computational tools with these kind of questions of the regularity of the cutting pattern. So this really fuels the research question. Can the use of contemporary mesh segmentation methods expand the design domain for pneumatic membranes, with particular attention to the cutting pattern and relations between material, patch, and global geometry? Here are the established design methods. The cutting pattern problem statement is one of trying to minimize deviation from the intended to the made. We've got a general workflow which is about form finding, analysis, and cutting pattern. Of course, that's more nuanced because often there are feedbacks that are occurring or iterations. What's interesting down below is that the approaches to meshings reveal certain problems. So here we have a regular mesh which then becomes cut, and we lose that regularity through the cutting. Whereas on the other side, we have a predetermined mesh which anticipates a form already. So it's not particularly useful if you're trying to invent form. Our initial explorations of mesh subdivision towards free patterning are shown here, and our method of working was very much oscillating in a reciprocal way between physical production and digital prototyping. Our approach is broken down into 5 steps, possibly a couple of minor ones in between. But if we start our movie, we start with a given form. This is not form found. What we're doing then is converting that into a mesh. We're identifying areas of curvature using k-means. And then what we're doing is we're doing mesh walks to begin to join or to begin to subdivide those patches in relation to fabrication criteria to be able to make the patches. One of the interesting nuances when we see the movie up here, where we were beginning to test the making of membranes with the hexagonal artifacts of the mesh, we see we're not achieving a particularly good surface. And so this led to the requirement for doing some mesh relaxations around the naked edges of our patches. And we see that in operation here. In terms of the material, we were using a standard polyester coated material. We had particular limits from our local supplier on what was available, and this became a way of being able to further drive the patterning of our membrane. So we're using different strategies here, which might be about trying to converge colors or trying to keep colors as separate as possible. Once we've identified for the two membranes the color distributions, this gets then broken down to a series of flattened cutting patterns ready for laser cutting. And this being informed, particularly in relation to the detailing around the edge, by our master seamstress, Maria Toot. It took her single-handedly 2 weeks to sew the meshes, to sew the mesh together. And she did an absolutely wonderful job. In terms of the net simulation, there was some interesting work by Petrus, who's the second author on the paper, looking at interacting systems and operating those simulations in Kangaroo 2. The net topology was defined in a similar mode to the membrane, only this time we're trying to identify areas of lowest curvature, essentially in the saddles, as a way of being able to generate a kind of geometric purchase for the net to hold on to. What's interesting is we found that we had a deviation once we tried to put the physical net onto the membrane, but we were able to mitigate that through a laser scanning of the membrane to achieve a better fit of the net. In terms of evaluation, surface quality is a real primary measure of success. We're demonstrating here a kind of learning from our prototypes to then being able to achieve very smooth transitions. We've got full tension, no wrinkles from compression, and we're getting good interfacing with the restraining net. In terms of our approximation to design target, we see that we're getting a little bit off design target. As a kind of general figure, we're quite close, but you can see that possibly here the yellow is marking possible overinflation, and this is perhaps one of the critiques of not working with a simulation in terms of the original form. And here we're also seeing some deviation from target. In terms of our research findings, we see that we can achieve an arbitrary non-form-found design target with complex curvature, and it can be approximated by the cutting pattern developed using these mesh segmentation methods. We believe that the design domain of pneumatic membranes can be extended and expanded by using these tools. However, as demonstrated in their use, the relation between scales of consideration is really strongest between the scale of the global and the scale of the patch, and not so strong in relation to the scale of the material, which perhaps is a bit of a problem in terms of our broader research question in complex modeling. One of the other essential findings is that we required naked edge relaxation of the patches to be able to achieve the final surface quality. In terms of the research limits, the demonstrator was not designed or tested for the full spectrum of external loads. It was built for an exhibition and demonstrates the workflows and tools that we developed. And one of the other limits I feel is that we were not really looking at membrane performance in terms of yarn-to-yarn scale. And we understand that this is really one of the driving forces in terms of why we see regularity when we move to proper external use. But we do identify that there are certain architectural use domains that might be possible immediately with this kind of output. Like most pneumatics, they are lightweight, they're quick to erect, they're quick to demount, they're movable, and in this case we feel that we're opening up a new aesthetic domain in terms of visual engagement and formal expressiveness. What's always very nice is when somebody from a different discipline comes along and sees this and it resonates with them. So here we have a collaboration between Sita and Christian Vogel, who's an electronic composer, and he was producing a piece called The Ballad of Agneta and the Merman, and he was very interested in the idea of the pneumatic being able to be used as a dynamically reconfigurable architectural sonography. Now, where I was particularly interested in the ability to achieve nice surface, his intentions were really about starting to explore really indeterminate states of the membrane. And here we see a moment where Agneta and the Merman are in union, in a way a kind of metaphor of the project as a whole between the net and the membrane. And I'd like to finish by showing you a portion of the performance that was premiered at the Aarhus City of Culture earlier this summer. Thank you for your attention.